Hello everyone, Assalamualaikum and good morning. So in this session, I will start discussing on topic 4, which is frequency response method. So this topic 4 is actually the fourth topic out of 5 topics to be discussed in this control system lecture. So basically, in our previous session, we have discussed on the root locus. So root locus is one of the methods on how we can do the plot of locus on the S-plane so that we can observe the behavior of a system in terms of stability. For example, the root locus gives us the information of the performance of the system transient response. So far for root locus, we have been focusing on the system transient response, meaning that as the poles move to the left-hand side of this S-plane, we will see that the system becomes more stable. For example, as you can see in this graph, different location of the poles, you see that the transient settling time is much more faster for the graph to the left-hand side compared to the right-hand side, the right one. So this is about the transient response. Okay, so what frequency response method do as compared to the root locus is frequency response method is much more focused on the uh, steady state margin or stability margin. Okay, so if you have a look at these points on the introductory part, the first point is frequency response technique is a control system design approach that uses only the information of the open loop transfer function along positive imaginary axis. So as compared to the root locus method, we have been focusing on the left half plane of the real axis, okay, which is negative half plane of real axis. But for the frequency response technique, if we refer to the S-plane, actually we are focusing on the positive imaginary axis. Positive imaginary axis, as you can see in this lecture notes, the location of the positive imaginary axis, meaning that start from 0 to the infinity of the imaginary axis j omega. That is the frequency response technique do. All right. So back to the point number 2 here, root locus give us direct information on the performance of the system's transient response, while frequency response give us the information of the steady state and stability margin. What I have said earlier, that this is ulang saja ya. Root locus, maksudnya root locus give the information of transient response. But for the frequency response method, it gives the information of the steady state and stability margin. So that is why as an engineer, as a control engineer, for example, what suppose that we should know is it is better for us to study both. It is better for us to know both the root locus technique and also the frequency response technique, because it covers different things. It covers different things in terms of transients and steady state. Steady state lah. Alright. So the root locus technique and frequency response technique actually complement each other. So basically what frequency response cover is the entire frequency spectrum. As you can see in this lecture notes, it should cover the top half plane of the imaginary axis, start from 0 to the infinity. Okay. So let's move on to my lecture notes here. Okay, actually I have covered the first part and then the other part. So the frequency response technique as written here, control system design approach that uses only the information of the open loop transfer function along positive imaginary axis. What has been given in the lecture slide as well. Okay, the same thing here. So as an engineer, you should know both, which is the root locus and also the frequency response technique, because these two technique covers different thing. Root locus cover more on the properties of the transient, but for the frequency response, it actually covers the steady state and stability margins of the system's performance. So by definition, what is frequency response analysis? What is frequency response analysis? You can read this. The frequency response of a system is a frequency dependent function. We have the function of the transfer function actually. G of S. G of S. Basically, what we do for S is we substitute S with J omega, which is omega is the frequency. So it is a frequency dependent function which express how the sinusoidal signal. So we focus only on the sinusoidal signal, repetitive signal like sine wave. So we are not talking about the ramp function, impulse, pulse, for example. But for this frequency response analysis, basically we are going to look into the steady state and stability margin, steady state performance of the system. We only focus on the input and output as a sinusoidal signal. Okay, sinusoidal signal of a given frequency. Given frequency mean at a certain frequency, we observe, let's say if we put the input of sinusoidal function and we observe what is the sinusoidal function behave at the output at particular frequency. Okay, at particular frequency. So what actually changed? What actually changed when we put the sinusoidal waveform at the input of the system? The properties that change when we do the excitation at the input. Okay, as you can see here, if we have a system with GS, we have the transfer function of the system G of S, and we have input of XT. We have input of XT and output of YT here. We call the output as response. Output response means output. Excitation means input. So we give input of XT as a function of time function of sinusoidal waveform. And then how the XT behave at the output. So we get the output of YT, also time function of the response. So basically, we expect that this is also the sinusoidal waveform. So, okay. So in this case, if we have this sort of system, if we give the input of sinusoidal waveform, the yellow one here, if we give the input of sinusoidal waveform, we will observe the output of the red one, which is YT. So XT input and YT as output. So the properties that change only the amplitude at the output or response, we will see that amplitude will change, and also the phase angle of the sinusoidal waveform at the output will be changed here. What is the properties that doesn't change? Here we see clearly that omega doesn't change. See that the frequency don't change, but the change, the properties that change are only amplitude and phase angle of the system. So based on this input and output relationship, when we excite the sinusoidal waveform at the input XT, and we see the response YT here, we can say that we can have a frequency response data when we vary omega from 0 to infinity. And also we can measure the magnitude. Also we can measure the magnitude using the equation here, which is this is the equation that we normally see when we want to find the magnitude, meaning that we put the lines here, which is magnitude of this function, and it is equals to B divided by A, which is output, magnitude of the output divided by magnitude of the input function. And also the phase angle can be defined as G j omega. Phase angle of the G j omega is phi equals to arctangent imaginary part of the G and divided by real part of G. So if you don't remember this sort of equation or formula, you can have a look in the textbook, Dorf textbook, page 566, which is the theoretical explanation about how we can represent the magnitude and also phase angle of a function like this. So if we have substitute S by j omega, because this is frequency function, we will get r omega plus jx omega, where r omega is the real part of the j omega, g real part of g, and jx omega is the imaginary part of g. Then we can represent it like this in the form of magnitude and exponential function of the angle, and then we can also represent in terms of magnitude and angle like this. It's a function of the frequency. And so to define or to determine the magnitude and frequency, basically we can use this formula. Okay, the formula for the magnitude and the formula for frequency. That is what we normally do for the function. Do you remember when you learn about the polar plot? Polar plot. So for this real part and imaginary part of the system, you can determine the magnitude and phase angle by using this equation. So basically, in a control system, we can represent the behavior of the system by using the polar plot. That is the alternative to the that is the common thing we can do for the frequency response. So when we talk about frequency response, we can represent it graphically by using polar plot. So this is example of the polar plot. We have the real part and imaginary part. Then we do the plotting on this axis lah, two axis. Okay. So basically, if you go through the examples given in the textbook, you will see this simple example of an RC circuit. So we have RC circuit here with output of V2 and input of V1. How do we represent this as a function of frequency? As we increase the frequency, what will happen to the output of the system? You will see that as we vary the frequency from 0 to infinity here, for this particular function, real part and imaginary part. Real part represents the resistive component, imaginary part represents the capacitive components here. So what we see, the locus or the frequency response plot in terms of polar plot here, when we vary the omega from 0 to infinity, and you'll see that the G is changing. G is changing. The magnitude is changing, as well as the phase angle also is changing based on this locus. All right. So that is the thing what has been discussed and described by the textbook. Okay, about some of the examples given in terms of polar plot. How do we represent the frequency response of a system? So in this topic, actually what I'm going to cover is not to cover the whole thing, including the polar plot, because we are going to focus the scope of this lecture, the scope of this course is only focused on the body plot ataupun boat plot. I will call it as boat plot. Some people call it as body plot. So I will keep for basically I will use boat plot. Okay, I will pronounce boat plot, not body plot. Boat plot. Okay, moving on to the lecture notes to the okay, so we have covered that. So basically the relationship between input and output, the yellow one is input. What we see at this frequency omega 1, for example, if we put the input, we excite the system with yellow signal, then we will see at the output the excitation, uh, the response, sorry. If we excite the system with yellow signal, the response of the system will be the red one. So basically the frequency is the same, but the magnitude and also phase angle now change. Similarly, at another frequency, okay, at another frequency omega 2 here, if we excite with yellow one, then we'll see at the response of the output as the red one, the red signal. See, both magnitude and frequency, both magnitude and phase angle now has been changed in this system at another frequency of omega 2. Similarly, for another frequency of omega 3, if we excite this system using the yellow signal, sinusoidal waveform of the yellow signal here, and then you will see at the output, which is the response of the system as another function of sinusoidal waveform, but different in terms of magnitude and phase angle. All right, so as you can see here, as we vary omega, this is one omega, this is another omega, another frequency, and this is another frequency. We can see the change of amplitude and phase angle. So how about if we change the omega from 0 to infinity? That is what we are going to observe in terms of the change of magnitude and also the change of phase angle of the system when we vary omega from 0 to infinity. So how do we represent that is basically we use the boat plot. So we use the boat plot to observe the curve or the behavior of the system in terms of magnitude and phase angle when we change when we vary the frequency from 0 to infinity. Okay, so at different frequencies, meaning that the output, the response is different in terms of phase angle and magnitude. Okay, basically this doesn't change shape means that the frequency is the same. What happened was change in amplitude and phase only. So in control system frequency response analysis, there are several methods has been introduced from the past researchers, from the past scholars. For example, the polar plots, as we have seen in the discussion a little bit about the textbook have discussed here, the polar plot is the first one. The Nyquist stability criterion, if you want to see the explanation or read further about Nyquist stability criterion, you can also check it in the textbook. There's also discussion about Nyquist stability criterion. So we have polar plot, Nyquist stability criterion, the second one. The third one is boat plot. So we are going to explore more on the boat plot in this particular topic for discussion. So basically in terms of history, okay, basically in terms of history here, the frequency response methods has been developed in around 1930 to 1940, which is at that time some of the researchers, some of the scholars like both nama orang Nikes and Nichols has established the method which is called the Bode plot, Nikes plot, and Nichols method. All right. So we are going to further explore on the Bode diagram method in our next discussion. But basically in this introductory part, for the Bode plot, actually, when we represent the Bode plot, actually the Bode plot cover both the conventional control theory and also the robust control theory, the modern one. All right. So Bode plot is quite useful when we want to observe the steady state and stability, steady state and stability margin of the system. So basically, when we talk about Bode plot, I think you have familiar with Bode plot when you follow the lecture of about the signal and system. For example, maybe there will be some discussion about how you can sketch the Bode plot or how you can compute the Bode plot of a system, of a given system, the given circuit, for example, using MATLAB. So you can use MATLAB as well to represent Bode plot. But basically in this course, we are going to explore on how we can do hand sketching or manually sketch the Bode plot using the given, based on the given problem. Because when we familiar with sketching the Bode plot, we will understand more. We understand further about the advantage of apa nama ni, sketching the Bode plot using hands. All right. So basically, this is the basic of the Bode plot, the basic of the Bode diagram. You will see that there is a frequency axis here. The horizontal axis represents omega, which is the frequency in log scale, logarithm scale. Log scale represent omega, which is the frequency. Okay, so log scale display wide range frequency on x-axis, on horizontal axis, and for the vertical axis, actually it is not log but linear scale. So horizontal axis is linear scale. So we call this as semi-log graph paper, because we have x-axis represented in terms of log, but the vertical axis or y-axis represented as a linear scale. So for the x-axis, basically it's a single variable, which is omega, which is frequency variable on x-axis. But on the vertical axis, we can represent both the magnitude plot and also phase angle plot. Okay, so vertical axis represents the scale for magnitude and the scale for phase angle, different scale actually, but using the same y-axis, meaning that we have two scales, one scale for phase angle, one scale for magnitude, which is gain. Another thing, basically when we call, when we talk about magnitude, it's actually the gain representation of the system. Okay, so with this Bode plot, actually we can observe the change in magnitude and phase across the entire spectrum of omega. Okay, so magnitude, the unit is represented in the form of decibel, dB, which is the gain. The gain and phase angle represented by angle degree. Phase angle represented by unit angle, which is degree. And y-axis is shaped by the magnitude and phase angle. Okay, but different scale lah, different scale and units lah. So that is the basic, the introduction about the 4.1 introduction about the frequency response, frequency response introduction. So I'm going to finish this video up to this time, just only to cover about the introduction saja. Alright, so that's all. I will continue on video 4.2 to discuss about frequency response diagram ataupun both diagram of the frequency response method. Alright, so that's all. Thank you.